Okay, inner solar system. And away we go, to quote John Wick. So let's talk about inner solar system, basically solar system inside the orbit of Jupiter, also the terrestrial planet region of the solar system. So I'm going to focus on the asteroids, and I'm going to discuss them from a recent perspective, except for this introduction, where I'm going to show you the way in which the asteroid belt has been unveiled as a function of time. So this will relate back to the early discussion about the impact of technology on the discovery rate of things in general. So here's a plan view of the solar system showing the orbits of the terrestrial planets in the middle, sun's in the middle, and then the ellipses around that are the planets, of course. The big circle is the orbit of Jupiter, 5 AUs in radius. The green things are basically the main belt asteroids. The blue things on the orbit of Jupiter are the Jovian Trojans, and these 2 banana-shaped clouds, 60 degrees ahead of Jupiter and 60 degrees behind. And the red things are asteroids which have escaped the asteroid belt and are planet crossing. So they're near-Earth asteroids. They're things that might hit terrestrial planets. Okay, so that's just a plot of the objects known. So let's see how these were discovered as a function of time. The first object was discovered in 1801. So Ceres is the first asteroid, and there is Ceres. And through the early part of that century, a few more asteroids were discovered by people looking through telescopes. Halfway through the century, photographic plates began to be used and more objects were found. But as I mentioned, photographic plates are not that good for observing asteroids because of trailing, because they're very insensitive. You have to integrate a long time. And so only a few hundred were known by the end of the 19th century. And the rate of progress was relatively modest, even through most of the first part of the 20th century, until the advent of electronic detectors on telescopes about now, causing this sudden surge in the number of asteroids known. Until present day sample is about 600,000 asteroids, a big fraction of 1 million asteroids, most of which are bigger than a kilometer or so in the asteroid belt. So there you can see pretty dramatically this increase in the number of known bodies from 0 in 1800 to 1 to a big fraction of 1 million today. Now let's take that distribution of asteroids and turn it so that we look at it sideways on. And you can see from the side, the asteroid belt is not a thin disk, so it's a bit like the Kuiper belt in that regard. It's more like a donut. It's a fat donut. And that is an indication of the intrinsic velocity dispersion in the asteroid belt. The Kepler velocity at 2.5 AU is probably 20 kilometers per second. So they're going around at about 20 kilometers per second. But the velocity dispersion, the typical velocity with which asteroids collide, is about a quarter of that. And that means that the vertical extent is about a quarter of a radian, something like that. So a quarter of a radian is 15 degrees or something. So the asteroid belt is all fluffed up, as you can see very clearly in that diagram. Now let's take the same diagram and collapse it sideways. So squash it down into a plane where we are plotting basically just the distance from the sun along the x-axis and the inclination of the orbit along the y-axis. And so you can see the asteroids are quite clearly cut up. And so the distribution is cut by these vertical dark bands. Those are the major resonances with Jupiter. Most of them are resonances with Jupiter. And you can see that the distribution of asteroids is highly non-uniform. It's very blobby. And those blobs correspond to collisionally shattered asteroids. So asteroids were formed, their inclination distributions were pumped up, and then they were smashed by mutual collisions that broke them into pieces, producing these asteroid families that basically preserve the inclination pretty well after the collisional shattering event occurred. Now, we see families of asteroids that were produced less than 1 million years ago, up to billions of years ago. When they're billions of years old, we're not really very sure, very confident about the accuracy of the age, but they're really old. They're a big fraction of the age of the solar system. And these families contain many, many thousands, tens or hundreds of thousands of objects per family. So that is, sorry for the drink, my throat is beginning to give out after all this talking. Now, when we look at these asteroids, we can do more than just measure their orbits. We can measure their colors. And so this has been done ad nauseum, really, since the 1970s, but more and more with time. And so here's a classic paper by DeMeo and Carey from 2013 that shows the distribution of different colored asteroids as a function of semi-major axis. Now, I have to say, this is one of the ugliest figures I've ever seen. I mean, these people have no sense of a good color scheme, or it's just a really ugly figure, but it does show, I suppose, the distribution of the different color types. So the red ones are the so-called S-type asteroids, which we think are probably counterparts to the chondrites, so the ordinary chondrites. And the blue ones show the so-called C-type asteroids that are probably closer to the carbonaceous chondrites, the more volatile, rich chondrites. And the figure shows that both types actually are quite widely distributed through the asteroid belt, but there's a small tendency for the red ones, the S-types, to dominate on the inner edge of the belt near 2AU. So the red curve is higher than the blue curve near 2AU. And then the opposite is true on the outside edge of the belt. The blue curve is higher than the other curves out there. The other colors, the green, the horrible green, the purple, and the K, those are other spectral types. We don't care too much about those. So the S-types are spectrally distinct from the C-types by having slightly redder colors and usually slightly higher albedos than the C-type. So they're compositionally distinct, again, using this idea that color is some kind of a measure of composition. In the asteroids, though, it's better backed up than it is in the Kuiper belt because the objects are much closer, and there are many, many brighter objects in the asteroid belt than there are in the Kuiper belt. Now, the correspondence between S-types and the chondrites, the ordinary chondrites, and the C-types and the carbonaceous chondrites is a little less simple to make than you might expect. And the reason is this thing called space weathering. So the idea is that when you crack open a meteorite and take a spectrum of a meteorite or measure the colors of a meteorite, what you see is a fresh surface. But when you take a spectrum or measure the colors of some asteroid in the asteroid belt, what you're seeing is a weathered surface. And the weathering in space is caused by things like, the solar wind banging into the surface of an asteroid, the cosmic rays hitting the surface, and so on. It's a long-term evolution of the surface. There's micrometeorite bombardment and so on. And so that has rendered the connection between asteroid spectral type and meteorite type a little bit uncertain for a long time. And is part of the justification for missions like OSIRIS-REx, which is out there picking up a piece of an asteroid to bring back home now. I mean, the objection to missions like that was, well, how stupid, you're going to go and get a piece of an asteroid, you're going to bring it back to the Earth, so what? We already have thousands of pieces of asteroids on the Earth called meteorites. They're in museums, you can just get them for free, basically. Why send a mission? And the answer really is, well, we don't know exactly where those meteorites came from in the asteroid belt. We know they're from the asteroid belt, but where exactly, which asteroid, we usually cannot tell. So by bringing back a sample from a particular asteroid with a spacecraft, we have absolute confidence where it came from, and we can make these connections between spectral types and composition of real meteorites. Now, a reminder is in this diagram from a paper by Paul Warren that the isotopic natures of meteorites are bimodally grouped. There are two groups, at least two groups in this diagram. And the particular isotopes don't matter. Isotopes in general, just a detail. But the point is there are two groups that correspond to the carbonaceous chondrites and to the other chondrites, the ordinary chondrites, we'll call them. And so the suspicion is that these two groups then correlate to the C-types and the S-types in the asteroid belt, okay? And the reminder is that these two isotopically distinct kinds of meteorite imply the existence of separated, spatially separated reservoirs in which these bodies formed. Conceivably one beyond Jupiter and one inside Jupiter, separated by Jupiter, but maybe has some other cause. We don't really know. So I just put that in there as a reminder. We'll come back to that in a moment. Now then, asteroid belt has been there, it's been studied since the first one discovered in 1801. So everybody and his dog has looked at the asteroid belt. It's been studied with every possible technique. It's been the proving ground for dynamics for hundreds of years. It's been studied with every telescope that was ever built, as far as I can tell, including the Space Telescope, including the Keck Telescope, including the Palomar Telescope and the 100-inch and the 60-inch on Mount Wilson. Every damn telescope has looked at the asteroid belt, and everybody has looked at the asteroid belt for hundreds of years. You would think that everything is known about the asteroid belt, but that turns out not to be the case. And it's really amazing to me that it's not the case, because the asteroid belt really is only 2 AUs from the sun. It's like 20 times closer than the Kuiper belt, right? Which is 40 AUs away, so it's a factor of 20. And then 20 to the power of 4 is about 400 squared. It's about 160,000. So a given object in the asteroid belt is 160,000 times brighter than it would be if you put it out there in the Kuiper belt. So this is a really easy observational target. I mean, the asteroids are really nearby. They're basically as close as you can get without hitting us. In fact, some of them do hit us. Nevertheless, a few years ago, Henry Shea and I did discover a totally new thing in the asteroid belt, caught us by surprise, was not predicted or expected, like many of the things in astronomy, in science in general, but turns out to be pretty interesting. So I thought I'd talk about that. So we discovered asteroids which showed the properties of comets. They actually look like comets. They have coma and tail and all the stuff that you see with comets. And the question is, what are they? Are they actually comets, or are they something masquerading as comets? So we call them generically active asteroids, because they are asteroids dynamically, and they are active physically. We can see that. So this plot shows semi-major axis against orbital eccentricity again. The yellow dots is just a sample of ordinary asteroids in the main belt, and you can see the Kirkwood gaps again. So you notice the main belt is mostly between about 2 and about 3 and a bit AUs, just inside the 2-to-1 mean motion resonance with Jupiter, which is over there on the right at 5 AU. The blue things are comets, dynamically speaking and physically speaking. They are ejecting material, as comets do, and comets should. And the red things are this new population of body that we have identified, which consists of asteroids that are ejecting mass. They're active asteroids. They're actively ejecting material. And this to me is as surprising as if you went out into your garden and found a rock in the garden that, unlike all the other rocks in the garden, was somehow fizzing and just blowing out material. I mean, it's just amazing. How would they do that? So this is a field of active research, so far entirely with ground-based telescopes and space-based telescopes, but soon to be investigated by a spacecraft launched, I hope, by the Chinese in the next couple of years. So to answer that question, are they comets, we need to know what's a comet. And one of the surprises to me is that different people in the planetary science community, such as it is, had different working definitions of what comets are. So you can imagine these for yourself. What's a comet? Well, you could say a comet is an icy object. It's a thing with ice in it. That's got to be a comet. Or you could say, well, a thing that formed beyond the snow line. You know, we know where it formed. It's formed beyond the snow line. That's a comet. Or you could say, well, I'm just going to do it empirically based on what I can see. If it has a coma, it's a comet. If it doesn't, it's not. Or maybe I can do it by the size or shape of the orbit. If it's a big, long elliptical orbit, it's a comet. If it's a circular orbit, you know, in the asteroid belt, it's not. And each of these definitions, they're all operational definitions used by different people. Each of these definitions has its own fans, and they're all in use, unfortunately, which has introduced a lot of confusion about this subject. They all have problems. So the problem with the first one is we don't have a good way to measure the compositions of most objects. So using a definition that's based on composition is a bit pathetic. Second problem with the location of formation is we don't in general know where objects formed except through the application of models. But the models are complicated, dynamical models are complicated. They change all the time, they have many parameters, so we don't really know much about that. Measurable properties, yes, we can take a picture with a telescope, and if it has a coma, it's a comet, that's fine. The trouble is that that's instrumentally sensitivity dependent. So if you have a weak instrument on a small telescope, you won't see a coma. If you have a big telescope, you might see the coma. So then it depends on which telescope you're using. So that's not a great definition either. And then characterizing it by the shape of the orbit is okay, provided that that shape of the orbit is preserved through time. So people typically use this thing, the Tisserand parameter, which is a combination of the orbital elements, semi-major axis A, eccentricity E, and inclination I. And the idea is that during capture, this parameter is roughly conserved in the circular restricted three-body problem. Truth is, it's not actually conserved, but it's nearly conserved. Anyway, different definitions of comets that we need to keep in mind. So I like this diagram that plots two of these things. The Tisserand parameter is going horizontally, and whether an object has a coma or not is plotted vertically. And so the diagram is divided into quadrants. Tisserand 3 is the nominal dynamical dividing line between comets and asteroids. Okay, so bigger than 3, we call them asteroids. Less than 3, we call them comets. And so down there, when we have objects with a Tisserand bigger than 3 that don't show any coma, that's pretty unambiguously an asteroid by two different criteria. Up there, where you have Tisserand less than 3 and you see a coma, that's pretty unambiguously a comet by two different criteria. Down there, different kinds of comets, different flavors, people give names to subcategories and so on. Down there at the bottom, we see things which are orbitally like comets, so the Tisserand parameters are less than 3, but they don't show a coma. So we suppose that they are dead comets of some sort, maybe dead long period comets, dead short period comets, but they're dynamically comet-like. And until 2006 or something, the upper right quadrant of this diagram was unoccupied. And so that's what we've done. We've put bodies in there. The active asteroids, or a subset of those called the main belt comets, are the things that appear in the upper right. So Tisserand's bigger than 3, and they show some evidence of activity. Those are the things I want to talk about right now. So there again is that diagram showing you the distribution of these bodies that have Tisserand bigger than 3 and show comet-like activity. And that's what they look like. They look fuzzy. They look just like regular comets. In fact, I've done a test in some previous talks where I show pictures of things. Some of them are Jupiter family comets, some of them are long period comets, and some of them are active asteroids. And I ask experts, observational experts, which one is which, and nobody can tell. Nobody can tell. So they look the same. Okay, so what are the processes driving the activity? Well, we found a bunch. It's very surprising to me. We found a whole bunch of processes that can eject material from asteroids. And they were not previously noticed, you know. I don't even think the majority of them were considered as being observable things. So the first one is thermal disintegration. And this is best seen on an asteroid called Phaethon, which is a parent of the Geminid meteoroid stream. It's never been seen to be active except at perihelion, like in the 3 pictures on the left, where it shows evidence for a tail made of dust. Okay, so this is material being blown out of Phaethon at perihelion, and the deal is perihelion is very close to the sun. It's 0.14 AUs from the sun, and the subsolar temperature on this body at perihelion is about 1,000 Kelvin. So it's really, really hot. It's really hot. Okay, so it's 1,000 Kelvin at the subsolar point, but as the rotation, which is a 3.6-hour rotation period, rotation carries that hot point round to the night side, then the temperature drops by 500 degrees or something. So you have huge thermal cycling on this body from hot to cold, hot to cold, hot to cold, hot to cold, especially at perihelion. And that gives rise to the suspicion that this is mass loss due to thermal fracture, expansion and contraction on the surface of Phaethon. Okay, so Phaethon is too hot for ice. Ice would already have sublimated away, it would long be gone. It is subject to thermal fracture. Thermal fracture can eject particles with speeds slightly bigger than the escape speed from Phaethon, which is a few meters per second. So it's plausible that particles can be popped out. And in fact, on Phaethon, as soon as you detach a particle from the surface, it becomes subject to radiation pressure sweeping, meaning that the radiation pressure force on that particle is bigger than the gravitational attraction to the nucleus. And so particles that are not too big can be simply pushed away from the nucleus just by radiation pressure, even if they're released at 0 velocity, as long as they're detached from the surface. So probably thermal cracking. The other possibility is called desiccation, and desiccation is a fancy word for drying out stuff. So there are lots of minerals that contain water, and when you heat them up to temperatures, 1,000 Kelvin for sure, but even 700 Kelvin, then they begin to dehydrate. And when they dehydrate, they shrink. And that's exactly what you see in a lake bed. A dry lake bed gets all cracked. And when the cracks form, the contraction cracking is maybe 10, 20%. There's a lot of fracturing and dust production from the cracked regions. And that could also be happening on Phaethon. Now, this was at first an interesting thing. It's like, okay, that's an interesting freak. It's just a detail. But since we did the observations of Phaethon, this very interesting paper by Granvik et al. Came out, in which they noticed that the number of asteroids coming in close to the sun, so the number of asteroids with a perihelion less than a few tenths of an AU, is much smaller than you would expect from a dynamical model alone. And so if this is actually a real detection of a depletion, as seems likely, it may be related to the Phaethon phenomenon. And it may be that any asteroid that goes close to the sun is quickly destroyed by thermal fracture. It literally splinters itself into dust, and then the dust is blown away. Okay, so there's a connection between the single example, which we discovered like a decade and something ago, and then this more recent discovery based on a dynamical model of the solar system, that there don't seem to be enough asteroids with very small perihelion in the solar system. Okay, I'll skip over that. So back to that diagram, we only have that one good example where thermal fracture is the likely mechanism responsible for comet-like activity. What about impact? Well, sure, makes sense. Asteroids should bash into each other, and when they do, they're going to collide at high speed, and they're going to smash each other. They're at least going to make a crater, and they may completely fracture each other. So the first example that we found was in 2010. This thing called 2010 A2 is a previously unknown asteroid. It's previously unknown because it's only 100 meters across. It's out there in the asteroid belt at the inner edge at about 2 AUs. It was too faint to have been seen before it suddenly ejected all of this debris. We measured the debris with a space telescope. We find that there's a very, very small velocity dispersion in this material, less than a meter per second. This is stuff just coming out very slowly and then being pushed back by solar radiation pressure to make that long tail. And in that tail, you can see that the upper right particles are about 1 millimeter in size, And down at the lower left, they're several centimeters and larger in size. And if you look at the magnified view, you can see clumps. Those are bodies that are probably even bigger, maybe meters or even tens of meters in size, being pushed back very slowly relative to the main nucleus. So that's the first example where we've seen an impact just after it happened. This was taken about 9 months, I believe, after the impact occurred. There you can see arrows where I've pointed to some of the discrete fragments that you can see in this fractured asteroid. In the same year, amazingly, we saw another example of impact. This is nothing like this has ever been seen before. This is a huge asteroid. It's not 100 meters in size. It's 100 kilometers in size. It's a biggie. This was discovered in 100 years ago by some guy with a pair of binoculars standing in the middle of the street in London. This is a really big, bright asteroid, absolutely boring for the last 100 and something years until it suddenly emitted this burst of dust in the end of December in 2010. And again, the explanation is an impact. It's an impulsive release of material. It's an impact consistent with the projectile coming in at 5 kilometers per second and a size of about 35 meters. So it's kind of, a big building size secondary body striking a 100 kilometer sized target. Whereas the first one was a 1 or 2 meter sized projectile striking a 100 meter sized target. So we suddenly started to develop the ability to see impacts in the asteroid belt, and that's potentially quite exciting because we can use these observations to really understand how impacts occur without relying on models. We can see what actually goes on, and we don't need to rely on models, and we don't need to rely so much anyway on impact experiments conducted at a tiny scale in the laboratory. So that's all good stuff. The timescales are quite surprising for all of this. So you know that the timescales are going to be long, and Botke and other people have worked out what the timescales should be given the known distribution and size distribution of asteroids. For the big guy, for Sheila, the timescale is about 10 to the 4 years. So we expect Sheila to be hit by this 35 meter sized projectile every 10,000 years, something like that. And you could say, well, what's the chance that you would see that? Since we're looking at the sky for only a small amount of time compared to 10,000 years. The point is that there are many, many asteroids. There are hundreds of asteroids as big as Sheila. And so the percent is more like a few percent per year. And we've been looking for, say, 10 years. So the chance of seeing a Sheila-like event is 10%. It's not that bad. For A2, it seems even more crazy. The impact timescale for disruption is something like 10 million years for such a small body. It's a small target, and it's going to be hard to hit because it's a small target. But there's a lot of 100-meter sized bodies in the asteroid belt. There's probably tens or hundreds of millions of bodies in the asteroid belt that big. And so the probability of seeing this event is not as bad as you might at first expect. This is a 100-meter body hit by a 2 or 3 meter sized projectile. So we've suddenly put ourselves in this new realm where we're looking at the sky quickly, frequently enough, and with enough sensitivity to see impacts as they occur. So the green triangles show which of those active asteroids are likely to be impacts. We've got 3 good examples and maybe a few more examples as well. There's also rotational instability. Now, this has been a hot topic for a decade or so because of the existence of a torque called the Yorp torque. And the Yorp torque is due to radiation. It's due to the anisotropic emission of thermal radiation from an asteroid that can exert a force called the Yarkovsky force and a torque, if it's a non-central force, as in general it will be on an irregularly shaped body. And that torque can change the spin. And in principle, it will just change the spin, accelerate the spin up and up and up and up and up until the thing is rotationally unstable and falls apart. And it'll fall apart because the tensile strength is pretty small if it's a rubble pile object. So I'm going for the world's record in the largest font, the largest font used in any equation in these lectures. So the Yorp timescale looks something like that. It's proportional to the square of the radius of the body and the square of the heliocentric distance. But at asteroid belt distances, it's a few million years for a kilometer-sized body, maybe 10 million years, something like that. So Yorp happens, and Yorp can change the spin, and Yorp conceivably can drive bodies to rotational breakup. And people have been thinking about that for at least a decade. But we have, in fact, begun to see examples of that, and I'll show you in just a moment. So here's the rotation distribution of asteroids as a function of diameter. The spin rate is plotted on the x-axis. The spin period is plotted on the right axis. So the spin rate goes up on the left, and the spin period goes up, downwards on the right, increases downwards on the right. And what you see is the most prominent feature is that for asteroids between about a kilometer, maybe half a kilometer, 200 meters, and a few tens of kilometers, there's kind of a tabletop. There's a flat top to the distribution of spin rates, as if there's some kind of a barrier. So it's called the spin barrier. And the belief is that this is due to a rotational instability, that when you spin an asteroid faster and faster and faster, eventually it's going so fast that it doesn't have enough gravity to maintain itself as a coherent body. So that spin barrier corresponds to roughly 10 rotations per day. It's about 2.5 hours, something like that, for asteroids. And obviously it's very well observed. There are very many asteroids in this plot from an excellent paper by Warner that I recommend you take a look at. Now, the main examples, the main counterexamples where you find very rapidly rotating asteroids are over there on the left amongst very small objects, less than a few tenths of a kilometer in size. And so there we think that those bodies are indeed spinning very quickly, and they're probably spinning very quickly because of Yorp, but they're spinning, and maybe because of just getting a kick by impact. But they're able to do that because they're strong. So these are kind of, think of an asteroid as being a bunch of grapes. The individual grapes are held together very weakly. They're attached very loosely, but the grape itself can be quite strong. So over there on the left, you're seeing the individual grapes that have been busted apart by impact or by spin from the bigger asteroid population. Over on the right, you see that the spin goes down, dips down relative to the spin barrier. And the thought there is that that's probably primordial. So it's a measure of the original spin that the asteroids picked up. And over there, for the big asteroids, the time scale for Yorp to change the spin is too long. And so it's the primordial spin that we're seeing. So this has been known for a while, but we have data. Oh yeah, this arrow just shows objects move diagonally on this diagram. So if you start with a kilometer-sized body, you spin it up and it breaks up, it's going to go diagonally. It's going to get smaller into fragments, and those fragments can accelerate by Yorp. We have examples. So this example came up in 2013. So this is like opening the door, and all these crazy objects suddenly rushed through the door. 2013 R3 is a main belt asteroid. The semi-major axis is 3 AUs. It's out there towards the outer parts of the asteroid belt that simply fell to bits. So you can see in this picture, which is kind of almost a discovery picture from the Keck, several bits. I've labeled them A, B, and C. But when you put Space Telescope on it, you can see several more bits. So each part is divided up. So there's just component A out of A, B, C. And component A from October the 29th to the 15th of November to the 13th of December, the 14th of January, expands and dissolves and breaks up into more and more pieces. So there's kind of a cascading fragmentation of the pieces of this body. And the most likely explanation that we can come up with is that this is a body that's been driven to some rotational instability, maybe by the Yorp torque out there in the asteroid belt. And we've seen it. Now we have supporting evidence for this from spacecraft. So this is the small asteroid Bennu, which has been visited by the NASA spacecraft OSIRIS-REx recently. And it's spinning, and it's got this funny shape, which turns out to be a characteristic shape for these bodies. It's kind of a diamond shape, or a muffin top shape, people call it. It's a small body, a few hundred meters across. But think of it as a body on which material is landsliding down towards the equator. So it's spinning fast enough, or it has in the past spun fast enough for surface instability to drive stuff towards the equator. So it's got a ridge around the equator due to the motion of material in that general direction. If it were spinning a little bit faster, presumably material would roll down, slide down, fall down to the equator, and then fall off, yeah, and just disappear, would just dissipate off into space. And that's probably what we're seeing in this object. That's my best guess. We're seeing an object that was spun up to a rotational breakup limit and lost material, and in fact lost pieces of itself. It fragmented into pieces. And then we have another example. This thing, 2013 P5, is an asteroid. None of these guys are normal asteroids, but well, they're normal asteroids, but they're not what we think of normal asteroids. This guy emitted 9 tails over 9 months, 9 separate dust tails. Each one is a discrete emission of dust, about 100 tons of dust per tail. They're not regularly spaced, but I think they correspond to landslides on the surface of a body rotating at the brink of rotational instability. And so the idea there is, think of a tray of sand. If you lift up a tray of sand, you tilt it. As you come up towards the critical angle, it doesn't all landslide at one time. You get little local instabilities where the slope is a little bit steeper here, or the material is a little bit weaker there. And so you have little landslides that go before the whole lot goes. So the model of this one is it's on the brink of a rotational failure. It's just dropping its regolith off into space. So we have several examples like that. There's the purple diamonds show the cases where I think the best explanation is rotational instability. So it's one of these completely new and amazing and unexpected things that we have discovered in the asteroid belt. Now, it's also interesting that some people believe the timescale for this rotational spin-up, the Yorp timescale, at small sizes, is shorter than the timescale for impact disruption of asteroids. And that may well be true. And what that means is these radiation forces, weak though they are, dominate the destruction of asteroids. So there's a kind of a collisional cascade down towards small sizes. And when they get small enough, the Yorp torque takes over and busts them apart. And so Yorp is actually the main destructive mechanism for asteroids in the main belt. And that means that the production of dust in the asteroid belt is dominated by Yorp. The production of meteoroid streams is probably dominated by Yorp. It's a very surprising thing. So it used to be all impact. Now it's some combination of impact and rotational instability in the main belt. Now, if there is ice present in the asteroids, and the next thing I'm going to say is that yes, there is. If there is ice present in the asteroids, then it can exert a torque like the Yorp torque, but 100,000 or 1,000,000 times stronger. And the torque, the time scale for spin up goes with a high power of the radius. So small bodies very strongly affected by this mass loss torque. And in fact, for 2013 R3, we can beat the Yorp torque if 2013 R3 is sublimating at a rate as small as 1 gram per second, which is absolutely undetectable. So the smallest amount of ice can spin a body up very quickly to rotational instability. So there's a whole bunch of stuff discovered recently in the asteroid belt just by looking. Again, these things, nobody said, go look and you'll find this thing. We just looked and we found these things. Very amazing. Now, what about real comets? Do we have real comets in the asteroid belt? The answer is yes. We call them main belt comets to distinguish them from just other active asteroids. So how do we know? Well, the main belt comets are repeatedly active. So they come to perihelion and they lose mass, and they go to aphelion and they stop losing mass, just like regular comets. So that indicates thermal control of the mass loss from these bodies, and sublimation is the natural explanation of that. The rates are very small, on the order of kilograms per second or less, and no gas has yet been detected in these bodies because it's beyond detection at such low rates. But nevertheless, this periodicity in the activity doesn't seem to have any other plausible explanation. Here's this case of 133P in a diagram by Henry Shea, showing that the places where it's observed to be active, the filled in symbols, all cluster around and just after perihelion. The perihelion is marked by an X with a P next to it. And then the other cases, the empty symbols, it was observed, but it was seen to be an asteroid, a point source. So they're active near perihelion when they're hot. They're inactive at aphelion when they're colder. And that's just what comets should do. We can calculate the mass loss rate from the energy balance equation. The absorbed sunlight on the left goes into some combination of radiation losses, the black body radiation, sigma T to the fourth, and then energy used to break bonds in ice, the sublimation energy, L is the latent heat, and then a bit of energy can be conducted into the interior. This water sublimation drops rapidly with distance from the sun. It's an exponential function of, actually it's faster than an exponential function of the temperature. But at 3 AU, where we see these bodies, you can still have significant sublimation rates. And in fact, 1 square kilometer of exposed ice can lose about 30 kilograms per second at 3 AU, which is rather extraordinary. The sublimation actually is so fast that you have to worry about the survival of the body. Can it really last there for, you know, a billion years, as it presumably has to? And the answer is yes. So there's work done by a number of people, but by Norbert Schorghofer in particular. And the work shows that all you need to do is put on a protective mantle, layer of porous dust, maybe 1 meter thick, maybe 2 meters thick, something like that. And you block the flow of gas very effectively. So the idea is that, just to get that into physical terms, you know, you can do an experiment, put some sand over your mouth. So face up, put a t-shirt over your mouth, and then put a layer of sand over your mouth and try to breathe through that. And the sand only has to be 1 centimeter thick, and you really struggle to breathe through the layer of sand. Or if you don't want to do it with sand because that's nasty, you can do it with a blanket. Get a blanket, just a blanket is a few millimeters thick. Try to breathe through a blanket. It's astonishingly difficult. You have to build up a lot of pressure to force the air through the tortuous, complicated pathways that go through the blanket, just as you would have to force the gas through a porous mantle on one of these asteroids. So I think this red thing is present on the asteroids, it's the mantle. And I think that the ice beneath is exposed by impact or some other process, maybe by a landslide. And then we have activity for a while before that exposed ice then seals itself off. The vent is covered up by more debris and the activity stops. And that means that the asteroids have a duty cycle. They're on for a certain fraction of the time, and then they're off for most of the time. And we have experimental constraints on that duty cycle. It's less than 10 to the minus 4. And that's pretty interesting because it means when you see an active asteroid, skip past that, when you see an active asteroid, because it's active for only 10 to the minus 4 of the total time, there are 10,000 similar bodies that you haven't seen because they're not in the active state. Yeah. And so when you look at it like that, it turns out that most of the asteroids, or all of the asteroids in the outer asteroid belt, could be ice-rich bodies in a dormant state. And they will, if you looked at it for a long time with a movie camera, you would see them flash on and off for a little while, like lights on a Christmas tree. So the idea is that basically the outer parts of the asteroid belt are ice-containing asteroids, in which case they really do satisfy many different definitions of being comets. So we think the outer asteroid belt is the third existing known comet reservoir after the Oort cloud and the Kuiper belt. We've got the asteroid belt that contains the main belt comets, which are these icy asteroids that have preserved ice against the heat of the sun for billions of years. Okay, we have additional evidence in support of sublimation. Again, even though the gas has not been detected, I can't think of any other explanation for this, this phenomenon. First of all, we see the repetitive activity just like regular comets. But second of all, we've detected non-gravitational acceleration in two of these objects, 313P Gibbs and 324P Lasagra. And that non-gravitational acceleration is due to the asymmetric ejection of mass. Only gas basically flies fast enough to carry enough momentum to have a recoil that we could measure on these bodies. You know, the other processes I mentioned can't do that. But the non-gravs are something that we see commonly in comets, and we also see it in at least these two of the active asteroids. And there's that reference to the paper by Norbert showing that ice can survive for a really long time, for billions of years, beneath the most modest mantle of dust. Lastly, the outer belt is suggested by Morbidelli and other people to be a place from which the Earth and terrestrial planets acquired some of their volatiles, maybe most of their volatiles. So the oceans, for example, probably didn't come from comets. There are various reasons to think they didn't come from comets. They more probably come from the asteroid belt, not from the existing asteroid belt, because again, the asteroid belt is a faint shadow of its initial self. It's lost a lot of mass. But we probably acquired some volatiles from things like the main belt comets in the early days of the solar system, maybe during this clearing phase when the asteroid belt was cleared out. And if we like this picture of, two reservoirs, we might like to identify the main belt comets with the outer reservoir, the one that supposedly was beyond Jupiter, which captured lots of volatiles, captured lots of water, and then were somehow scattered inwards and then placed into the asteroid belt from the outside. But we haven't established that last thing yet. The thing in red would be nice if it's true, but we haven't yet shown that to be true. So there are the bodies that appear to be sublimating based on the indications I've mentioned. They're mostly in the outer parts of the asteroid belt, those big blue stars. So that's really what I wanted to say about the inner solar system. I think that's all extremely fantastic. I think it's amazing that you can find anything new in the asteroid belt, given that the asteroid belt has been studied for so long by everybody with everything. But apparently you can. And so the moral there is you just got to look. And the more you look, the more you see. Okay.